Have you ever wondered how recursion works in programming? Well, recursion is a fascinating concept that might seem a bit tricky at first, but once you get the hang of it, it's a game changer. It's like a magical loop, but with a twist. Instead of repeating the same action over and over again, a recursive function calls itself, diving deeper into smaller and smaller tasks or problems. It's a method where the solution to a problem depends on solutions to smaller instances of the same problem. Imagine having a big puzzle, and instead of trying to solve it all at once, you break it down into smaller puzzles, each resembling the original one. That's recursion for you. It's about solving big problems by tackling smaller, more manageable ones. Sounds complex? Don't worry, we'll break it down together. A recursive function has two main parts, the base case and the recursive case. Now let's delve a bit deeper into these two crucial components. The base case is the simplest form of the problem, the instance that we can solve directly without any further recursion. It's our way of telling the function, hey, you've done enough work. It's time to stop calling yourself and give us an answer. The base case is our safeguard against infinite recursion, the programming equivalent of a hamster wheel that just keeps spinning and spinning. Without a well-defined base case, our function would keep calling itself forever, leading to a stack overflow and, ultimately, a crash. On the other hand, the recursive case is where the magic truly happens. This is where our function rolls up its sleeves and gets to work, calling itself to solve a smaller instance of the same problem. Each recursive call should bring us one step closer to our base case, like a mountaineer inching closer to the summit with every step. It's like a Russian nesting doll. Each recursive call peels away one layer, revealing a simpler version of the same problem. We continue to peel away these layers until we reach the smallest doll, our base case, and then we start piecing everything back together. Think of it as a chef breaking down a complex recipe into simpler steps. The base case is the final dish, ready to be served, while the recursive case is the chef working through each step, chopping, mixing, and cooking until the dish is ready. Let's not forget that recursive functions, like all good things, come with their own set of challenges. They can be hard to debug and can lead to performance issues due to the overhead of additional function calls and stack usage. It's a trade-off between simplicity and efficiency, elegance and power consumption. So whether you're calculating the nth Fibonacci number, traversing a binary tree, or finding your way out of a maze, remember this. A recursive function is a chef, a mountaineer, and a Russian nesting doll, all rolled into one. And most importantly, remember, a recursive function is only as good as its base case. Let's dive into an example to make things clearer. Consider the mathematical operation of finding a factorial. In mathematics, the factorial of a non-negative integer n is the product of all positive integers less than or equal to n. So the factorial of 5, for instance, is 5 times 4 times 3 times 2 times 1, which equals 120. Now, how do we implement this using recursion in a programming language like Python? Let's see. We start by defining a function, let's call it factorial, which takes an integer n as an argument. Now we need to establish our base case. In the case of factorials, the base case is when n equals 0 or 1. Why? Because the factorial of 0 and 1 is, by definition, 1. So within our function, we start by checking if n equals 0 or 1. If it does, we simply return 1. This is our base case. But what if n is greater than 1? Here's where the magic of recursion comes in. We return the product of n and the factorial of n minus 1. Yes, you heard it right. We're calling the factorial function within itself. This recursive call continues the process, each time with a smaller value of n, until we hit our base case. When n equals 0 or 1, the function stops calling itself and starts returning values up the call stack, until we get the final product, the factorial of the original number. Let's run through a quick example. If we want to find the factorial of 3, the function first checks if 3 equals 0 or 1. It doesn't, so the function calls itself with the value 2. The process repeats until we hit the base case when n equals 1. Then the function starts returning values, giving us the factorial of 3, which is 6. And that's how a simple recursive function works. Like everything in programming, recursion has its strengths and weaknesses. Let's start with the strengths. One of the most significant advantages of recursion is its readability. Recursive solutions can often be more readable than their iterative counterparts, as they provide a clear, direct translation of the problem's description into code. This readability can make your code easier to understand, which is a huge benefit when you're working on a complex project or collaborating with a team. Secondly, recursion can simplify complex problems. By breaking down a problem into smaller, more manageable subproblems, recursion can make even the most daunting tasks seem approachable. It's like tackling a giant puzzle piece by piece. Each recursive call is a step towards the solution, making the journey to the final answer a whole lot smoother. But of course, recursion isn't all rainbows and sunshine. It has its downsides too. One of these is the performance overhead. Recursive functions can be more resource-intensive than their iterative counterparts due to the additional function calls and stack usage. This overhead can slow down your program, especially if you're dealing with large inputs or making a lot of recursive calls. So while recursion might make your code more readable, it could also make it less efficient. Lastly, there's the risk of infinite recursion. If you don't define a proper base case or your recursive calls don't move towards the base case, your function could keep calling itself forever, resulting in an infinite loop. This could lead to a stack overflow, where your program runs out of memory and crashes. It's like falling into a rabbit hole with no bottom, not a fun experience. So, recursion is a bit of a double-edged sword. On one hand, it can make your code more readable and simplify complex problems. On the other hand, it can lead to performance overhead and infinite recursion. As with most things in programming, it's all about balance. You need to weigh the pros and cons and decide whether recursion is the right tool for the task at hand. So, it's all about using the right tool for the right job. Recursion is more common than you might think. It's like a secret weapon, often hidden in plain sight, ready to simplify complex problems. Let's delve into a few examples where recursion really shines. Firstly, consider the Fibonacci sequence. This mathematical series is defined such that each number is the sum of the two preceding ones. To calculate the nth Fibonacci number, we can use a recursive function. The base case is when n equals 0 or 1, and the recursive case is the sum of the two preceding Fibonacci numbers. This is a classic example of recursion at play. Next, let's talk about binary search. This is a search algorithm that finds the position of a target value within a sorted array. It compares the target value to the middle element of the array, and based on that comparison, eliminates half of the search space. This process is repeated recursively on the half where the target value could be until it's found. Moving on, tree traversal is another common problem solved with recursion. In computer science, a tree is a widely used abstract data type that simulates a hierarchical tree structure. Traversal involves visiting each node in a specific order. Whether it's in order, pre-order, or post-order, recursion makes this task a breeze. Finally, consider maze solving. You're probably familiar with the concept of a maze, a complex network of paths where the challenge is to find a route from start to finish. Recursive backtracking is a method to solve such mazes. It involves exploring each path. If at a dead end, it steps back and tries another path and so on, until it finds the exit. As you can see, recursion can be a powerful tool for solving a variety of problems. It's like a little magic trick, turning seemingly complicated tasks into simpler, manageable ones. So the next time you're faced with a complex problem, don't forget to consider recursion. It might just be the secret weapon you need. We've come a long way in understanding recursion. We've explored how recursive functions are structured, with their base and recursive cases, and we've seen how these functions can elegantly solve problems by breaking them down into smaller, more manageable pieces. We've dived into the factorial function as an example, and seen how recursion can be used in a range of scenarios, from calculating Fibonacci sequences to traversing tree structures. But as we've seen, there are two sides to every coin. The beauty of recursion comes with its own set of challenges, like performance overhead and the risk of infinite loops. It's essential to strike a balance, understanding when to use and when to avoid recursion. In the end, recursion is more than just a technique. It's a mindset that encourages us to solve problems by breaking them down into simpler subproblems. So keep exploring, keep learning, and keep coding. Remember, recursion is not just a technique, it's a mindset. Happy coding!